Hello and welcome to the AI-MicroBMT end-to-end evaluation demo. In this video, we demonstrate the complete workflow of our benchmark framework, from downloading datasets and models to running inference evaluations to computing unified deployment scores or on a real hardware target. This demo is intended to show the practical reproducibility of AI-MicroBMT and end-to-end usability. For this demo, we will evaluate an NVIDIA Jetson Orin board using ONNX runtime as the inference backend. To assess the Orin backend, I will assess using SSH on Windows operating system. So let me check the architecture, which is ARM64, and this is the Ubuntu operating system. So if you haven't downloaded our platform on your machine, you can download it from this AI-BMT.com. Since I want to evaluate the Orin board on Ubuntu and ARM architecture, and I want to evaluate using the C++, so I can download this one and implement the interfaces in the main C++ file. But since I have already downloaded it here, so I'm not going to download it again. And I also implemented this main C++ file for Jetson board evaluation. So I will just directly evaluate it. You can also open VS Code here like this, but since I don't have to modify the code because I already modified, so I just open the README file and build it again and then execute it. Oh, I have to go to the build folder and then copy and paste these commands. So now this AI-BMT GUI will show up. This main C++, here I have already configured these hardware abstraction layer interfaces to support ONNX runtime on the Jetson platform for the classification task. Now one might ask, does ONNX runtime fully exploit the Jetson's maximum hardware capability? Not necessary. The vendor optimized runtimes such as the TensorRT may yield higher throughput. However, this is exactly the kind of insight our benchmark is designed to capture. How well a device supports widely used standardized runtimes like ONNX runtime is itself a meaningful dimension of hardware competitiveness and deployability. AI-MicroBMT can evaluate the same device on the different runtime backends, and the UDS metrics will reflect these differences. And this demo focuses on the image classification task using 67 microBMT models from our curated model suite. However, it is important to note that AI-MicroBMT is not limited to the classification. Our framework currently supports object detection with various models, and semantic segmentation, and LLM inference. And this LLM currently supported with vision task-like pipelines. We are actively refining the evaluation methodology to better capture LLM specific characteristics such as token throughput and time to first token. For this demo, we proceed with classification as it allows us to show the complete pipeline clearly. First, we download the evaluation dataset. Click this one. The dataset is a standard ImageNet v2 used for our benchmark. After this zip file is downloaded, it will automatically extracted to the format that can be directly used in our framework. And for next step, we will download our 67 classification Onyx models. So I will click this one. Now our models and datasets downloaded and ready for the evaluation. So we go back to the main page. And before starting the evaluation, let us configure the benchmark parameters. Since this is a quick demonstration focused on showing the evaluation workflow rather than producing publication-grade measurements, we apply the following lightweight settings. We will choose a number of samples as 120 instead of a full evaluation set. And we choose the repetition as 1 instead of 3. And we will disable the warm-up, and we will skip the dataset validation for the faster evaluation. And we will enable this database upload, which stores the result in a cloud database linked to the logged in account. This makes it easy to aggregate the result across multiple devices and sessions and multiple models. While we recommend this for convenience, it's entirely optional. And now I have to log in before the evaluation because I didn't skip this one. If I skip this one for evaluation, I don't have to log in because we will just evaluate locally and do not upload it to the database. But here we want to upload the result to the database for the easier evaluation later. So yeah, click this one and save current configuration and start. Because if I haven't logged in yet, it requires me to log in before the evaluation. So let me log in first. And then, yeah, now we select this one. This is the one that I just downloaded. There are 67 Onyx models. So select all 67 models and start the evaluation on the current configuration. Let me just stop it. I just made a mistake. Yeah, since I said I want to evaluate under single stream scenario first, so I will set this as a single stream and save the configuration and do it again. Yeah, since single stream evaluation is finished for the 67 models, we select this offline scenario and then evaluate the 67 models again for this offline scenario. Now the offline evaluation is also complete. We now have both the single stream latency and offline throughput measurements for our 67 models on JSON or in board. So as you can see, there's a result for 67 models for both offline scenarios and single stream scenarios. And as you can see here, accelerator type is NVIDIA JSON ORIN. This is very important because in this interface implementation, I gave this information to accelerate type. Other information is not that important, but this accelerator type information is very crucial because in our AI-MicroBMT analysis scripts, it will separate accelerator type by this column. So when you implement the interface, you have to provide this accelerator type information. And now I will save this as a CSV file. So maybe I can save it here. Yeah, maybe I can save it here. For example, I can name it as eval results, something like this. So it's successfully saved here. Oh yeah, it's not easy to visualize it. So maybe I can move this to, for example, I can make a new directory and In this directory, I will move this eval result CSV file here. I shouldn't give it the extension name CSV. Yeah. And as you can see, yeah, it visualized very well. And actually there are too many informations. From here is the previously measured results, so I will delete all of them. And as you can see, the number of rows is 134 because we measured 67 models, and for our single stream and offline, so is 134. So as you can see, the all evaluation results are successfully saved into this CSV file, I mean the database. And since we have already uploaded the data as a CSV file, so we can go to our AI-BMT.com and click this one. Then it will go to AI-MicroBMT repository. So I will just copy this one and clone it here. And let me move this file to AI-MicroBMT that I just downloaded. And then I will go to this folder and open VS Code here. So let's go to the README first. So here I already downloaded the requirement into my environment, so I will skip here. And I already go to AIBIM.com. I already evaluated it, and now I have the evaluation result, so I will skip this step. And yeah, I will start from here. So I have a evaluation result CSV, so I will run this one and go to the terminal. And I need to modify this CSV file as eval results. And then this config file, let me check. Yeah, I need to add this one to this old accelerator here. And then I need to choose a color for this. Maybe I can 333333 gray color here. Case analysis and view NVIDIA Jasonor in here, and here create the UDA's score hardware power. Okay, because I didn't check the hardware spec here, I will just give it a kind of random value. And for this peak compute, I also didn't check the hardware spec. This is just an arbitrary value just for testing. So yeah, we can start. Since we run this one, so as you can see here, we now have a JSON ORIN data already appended to existing files. So next, according to this README file, we can start to run this part and also this part. So yeah, let me run this part first. And then let me run this part. Because we didn't actually measure the input resolution variation test, so for the input variation, it doesn't include the JSON ORIN data here because we didn't measure it just for this simple demo. So let me check the produced results. For example, as you can see, the NVIDIA JSON ORIN result will be included here, the gray lines. And for this one, it have a kind of a weird result. That's only because all other platforms are evaluated under the conditions that are described in our paper, using the entire data set and repeat 3 times. And for this NVIDIA JSON ORIN data, we only evaluated 120 samples, which have a higher accuracy, so it have a kind of weird results compared to others. This is just for demo purpose, so don't care about the weird result because they are not evaluated under the same condition. I just want to show that it can produce results correctly using this kind of a pipeline. As you can see, you also have an NVIDIA just an orange result here. And because we didn't measure the resolution sweep for this quick demo, so it will not include just an orange data here. So, and finally the UDS matrix. And for this one, you can see that, yeah, you have a JSON orange data here. So we can see that it can produce the result well because it doesn't measure the resolution sweep, so the S3 scaling score is 0 for this NVIDIA JSON orange. So I will end my demo here. Let me summarize this demo. Today we computed the UDS subscores for NVIDIA JSON Orin under ONNX runtime, and the results provide a decomposed, interpretable view of the device's deployment readiness, not just a single swoop number, but a multidimensional profile covering coverage, accuracy, precision, speed, and scenario adaptability. And these scores can be directly compared against other devices evaluated with the same pipeline, enabling fair structured cross-device comparison under standardized conditions. Given the same hardware and runtime versions, this entire workflow can be independently reproduced. If you want to evaluate your device correctly and compare it with other devices, you have to evaluate under the official evaluation conditions that are described in our paper, which is evaluate on the entire data set and evaluate at least 3 times, evaluate all models in these conditions. We also need to evaluate input resolution variant test for specific models. And I know it will take a long time because there are so many models and so many configurations, but I believe that this kind of various configurations can precisely detect hardware characteristics, so you can see the pros and cons of a specific hardware compared to others. Thank you for watching.